Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on the McCabe-Thiele method. This will be the last part of my discussion on the McCabe-Thiele method. And as far as distillation is concerned, this is 35th part. Today I will be deriving Fenske equation. This is a mathematical expression that is used to find the minimum number of stages in a tray column when it is operating under total reflux. So I will derive the equation, and the other thing that I will be discussing in this video is I'll be talking about the limitations of the McCabe-Thiele method. What are the limitations of this method? Limitations of the McCabe-Thiele method we are going to understand in today's video. So let us begin. As I said, Fenske equation is used to find a minimum number of stages in a tray column, and minimum number of stages will come into picture when the tray column is operating under total reflux. So first, to begin with, let us look at the fractionating column that is operating under total reflux. So you have the column, you have trays in it, then feed. Enough feed is given to the column and then it is stopped. The feed solution is sent to the reboiler where it is heated to boil it to create the vapor phase. The vapor phase is admitted at the bottom of the column. It rises. Then it is removed from the top. It is taken to a condenser where the vapors are condensed, and all of the condensate is written back to the column as reflux. Then reflux flows down and joins the other liquid in the column. So in this way, when the column is operating under total reflux, there is no feed to the column, because initially enough feed is given to the column. Then no distillate is taken out and no bottom product is taken out. So a simple schematic of a fractionating column that is operating under total reflux, now you can see over here. No feed, that is F is equal to 0. No distillate, that is D is equal to 0. No bottom product, that is W is equal to 0. So there is no feed to the fractionating column. So if you have to describe a fractionating column that is operating under total reflux, then you can simply write these points. No feed to the fractionating column. All the condensate is written to the column as reflux. No distillate is taken out. Reflux ratio is infinite, because reflux ratio is the ratio of the reflux stream. This usually it is denoted by L0. So L0 upon D. And when D is 0, R becomes infinite. That is, when the column is operating under total reflux, reflux ratio is infinite. Then no bottom product is taken out, that is W is equal to 0. Then required number of stages to bring about the desired separation, they are minimum. Required number of stages are minimum. Then reboiler heat duty is maximum, that is heat required to boil the liquid solution is maximum. Similarly, condenser heat duty is maximum. The quantity of heat that is to be removed from vapor, it is maximum. Condenser heat duty is nothing but the amount of heat that is removed from the vapor in order to condense them. Okay. So no feed to the fractionating column. All the condensate is written to the column as reflux. No distillate is taken out. Reflux ratio is infinite. No bottom product is taken out. Required number of stages are minimum. Reboiler heat duty is maximum. Condenser heat duty is maximum. And in the McCabe-Thiele method, we have learned how to find the required number of stages, minimum number of stages that are required in this case. So we have learned how to find them graphically. I have discussed it in my previous videos. I'm giving link to those videos. Over here, you have to remember that when the column is operating under total reflux, the required stages, they are minimum. You cannot use less number than this minimum number of stages. Okay. Now, what is Fenske's equation? Let us know about the Fenske's equation. So, Fenske's equation, it is a mathematical expression that is used to calculate the minimum number of ideal stages. Again, this equation is going to give you the number of ideal stages. The Fenske equation is a mathematical expression used to calculate the minimum number of ideal stages or equilibrium stages or theoretical stages in a fractionating column when it operates under total reflux. So, the Fenske equation is a mathematical expression that is used to calculate minimum number of ideal or equilibrium or theoretical stages in a fractionating column when the column is operating under total reflux. It can be used again. You can use this equation the way it is derived. Based on that, you can use this equation when the components invert, they can form ideal solutions. Then and then only you can apply this Fenske's equation. So, this thing you have to remember. Fenske's equation is used if the components invert, they form ideal solutions. To understand it in a better way, let us consider an example. For example, if you have two components, which are these two components A and B, in which A is more volatile, that is boiling point of A is lower than that of B and its vapor pressure is higher than that of B. So, in order to understand the concept, we are going to consider two components A and B. A is the more volatile component. So, if A and B forms an ideal liquid solution, and when this solution is vaporized, if the resulting vapor mixture is also ideal, then you can use Fenske's equation. If the system involved in the fractionating system handled in the fractionating column is solution of two such components, which forms ideal solutions, then you can use Fenske's equation. So, in short, you can use Fenske's equation to find the minimum number of stages in a fractionating column if the column is handling ideal solutions. So, in practice, few solutions can be assumed to be ideal, and then in those cases, you can use the Fenske's equation. It is based on the Fenske's equation. It is based on the definition of relative volatility, that is alpha AB. So, what is alpha AB? This relative volatility, the equation, the definition that we are going to use to get the Fenske's equation, it is defined when the liquid solution is in equilibrium with the vapor mixture. For example, in our case, if you have liquid solution of A and B, and if this liquid solution is in equilibrium with the vapor mixture of A and B, then you can define the relative volatility. The relative volatility is defined at that point when the liquid solution is in equilibrium with the vapor mixture. So, the Fenske's equation, it is based on the definition of relative volatility, which is defined when liquid solution is in equilibrium with the vapor mixture. So, alpha AB is volatility of A relative to that of B. Alpha AB, this notation, it stands for, or it gives volatility of A relative to that of B. Now, let us understand the derivation. So, as I said, we are going to start with the definition of alpha AB, relative volatility. So, alpha AB for ideal systems, when they are in equilibrium, ideal liquid solution is in equilibrium with ideal vapor mixture, then for that case, alpha AB is defined by this equation. Alpha AB is equal to YA upon XA divided by YB upon XB. In this case, XA and XB, these are mole fractions of A and B in the liquid solution, respectively. And YA and YB, these are mole fractions of A and B, respectively, in the vapor mixture. And the liquid solution that we are talking about is an equilibrium with the vapor mixture of the same two components. So, this definition is applicable when this is satisfied. The liquid solution is an equilibrium with the vapor mixture. So, we are going to start with this equation. Since this is a binary system, sum of mole fractions in the liquid phase, that is XA plus XB, is equal to 1. That means from this you can get equation for XB in terms of XA. So, XB will be equal to 1 minus XA. Similarly, in the vapor mixture, mole fraction, sum of mole fractions is equal to 1. That is YA plus YB is equal to 1. And then you can have equation for YB in terms of XA. So, YB will be equal to 1 minus XA. Now, we are going to use this equations for XB and YB in the equation for alpha AB. That means we are going to write everything in terms of A. So, if we do that, equation for alpha AB becomes alpha AB is equal to YA upon XA divided by 1 minus YA upon 1 minus XA. So, YB is replaced with 1 minus YA and XB is replaced with 1 minus XA. Okay, so previously we got this equation alpha AB is equal to YA upon XA divided by 1 minus YA and divided by 1 minus XA. Now, for simplicity, I am going to remove the subscript. So, I will be writing the equation like alpha AB is equal to Y upon X divided by 1 minus Y divided by 1 minus X. That means, in this case, small y stands for mole fraction of A in the vapor phase and small x stands for mole fraction of A in the liquid phase. So, if I rearrange it, I will be writing like this. I will bring this term on the side. So, the equation will be alpha AB into 1 minus Y divided by 1 minus X, that is equal to Y upon X. So, further I will rearrange it like this, alpha AB into X upon 1 minus X. So, I'm going to bring this X on this side and then this X I'm going to take to the other side and 1 minus Y I'm going to take to the right hand side. So, if I do that, I can get this equation alpha AB into X upon 1 minus X, that is equal to Y upon 1 minus Y. So, that is nothing but Y upon 1 minus Y is equal to alpha AB into X upon 1 minus X. Now, if this equation is to be written for n plus 1th stage, a stage which is numbered as n plus 1, if this equation is to be written for that, then it will be written in this way, yn plus 1 upon 1 minus yn plus 1, that is equal to alpha AB into xn plus 1 divided by 1 minus xn plus 1. So, yn plus 1 in this case is mole fraction of A in the vapor phase, that is leaving n plus 1 stage, and xn plus 1 is mole fraction of A in the liquid phase, that is leaving n plus 1th stage. So, if you have to show it with the help of a simple schematic, you can show over here. So, if this is n plus 1th stage, then you have the liquid that is leaving it. So, the mole fraction of A in this, it will be xn plus 1, and then you have vapor that is leaving this stage. Mole fraction of A in it will be yn plus 1. Okay, so in this way, you can write the equation for n plus 1th stage. So, let me first erase this. I hope you have understood how we are writing the equation for n plus 1th stage. But At total reflux, what we know yn plus 1 is equal to xn. That is, the operating line for the rectifying section and then for the stripping section, both of them coincide with the diagonal line. So I have discussed this in my video on distillation under total reflux. I am giving link to that video. You please watch it if you have not seen it. So since the operating lines coincide with the diagonal line, you have this relationship yn plus 1 is equal to xn. That means now wherever there is yn plus 1 in the previous equation, I am going to replace it with xn. So if I do that, I'll be getting this equation. So what is this? Xn upon 1 minus xn, that is equal to alpha AB into xn plus 1 divided by 1 minus xn plus 1. So let us continue with this equation. So previously we got this equation xn upon 1 minus xn, that is equal to alpha AB into xn plus 1 upon 1 minus xn plus 1. Now let us look at the column, because we will need that diagram for our understanding. Now, what is the composition of the reflux? It is XD. Because if distillate is to be taken out, then it will be having composition XD. So now we are not taking out the distillate because it is operating under total reflux. So the reflux, in the reflux, mole fraction of A, that is mole fraction of more volatile component, will be XD. So XD, liquid with composition XD, is going to this stage, the topmost tray in the column, and I numbered that as tray number 1. Let me write it properly. So I will number it as tray number 1. Okay, so liquid with composition XD, it is going to stage number 1, flake number 1, and then a liquid stream will be leaving stage number 1, and that liquid stream will have composition of X1. Mole fraction of A in it will be X1. That means if I have to consider condenser in the first stage, that means if I have to write this equation for the combination of condenser and first stage, the equation will be written like this: XD upon 1 minus XD, that is equal to alpha AB into xn x1 divided by 1 minus x1, and I am calling it as equation 1. So if XD is said to be 0, XD, the tray, or we are talking about a tray before the first plate. So this is one plate. If you say X1 will be the next plate. So that means in this case, if Xn is XD, Xn plus 1, according to this, if you can refer this diagram, Xn plus 1 will be equal to X1. So that's why, or in this way, you get equation number 1. XD upon 1 minus XD, that is equal to alpha AB into Xn upon 1 minus Xn, X1 divided by 1 minus X1. I am calling it as equation 1. Next, I will consider first and second stage. First and second stages. So now on the left hand side, you will have information for the first stage, and then on the right hand side, you will have information for the second stage. So that means the equation now will be written as X1 divided by 1 minus X1, that is equal to alpha AB into X2 upon 1 minus X2. I am calling it as equation number 2. And now you can easily understand how the equation can be written for second and third stage. So now the equation will be written as X2 upon 1 minus X2, that is equal to alpha AB into X3 upon 1 minus X3. And now I am calling it as equation number 3. In general, if I go on and then write for n minus 1th and nth stage, so that means n minus 1th stage on the left hand side and nth stage on the right hand side. So if that is done, then the equation will be written like this. X n minus 1 divided by 1 minus x n minus 1 is equal to alpha AB into xn upon 1 minus xn, and now I am calling it as equation 4. So equation 1, it was written for condenser in the first stage. Equation number 2 is written for first and second stage. Equation number 3, it is written for second and third stage. And in general, equation number 4 is written for n minus 1th and nth stage. So we will be using this equation in our derivation. So previously we got all those equations. I am collecting them once again. So xd upon 1 minus xd is equal to alpha AB into x1 upon 1 minus x1, equation 1. Then x1 upon 1 minus x1, that is equal to alpha AB into x2 upon 1 minus x2, equation 2. x2 upon 1 minus x2, that is equal to alpha AB into x3 upon 1 minus x3, equation 3. And finally, for n minus 1 stage, that is xn minus 1 divided by 1 minus xn minus 1, that is equal to alpha AB into xn divided by 1 minus xn. And this is equation number 4. Now we are going to carry out one task, and the task is we are going to multiply all these equations together. So right hand sides will be multiplied and then left hand sides will be multiplied. So if you check the left hand side of the equation, that is this side, then if you carry out the multiplication operation, you will get xd upon 1 minus xd into x1 upon 1 minus x1 into x2 upon 1 minus x2 into the final term in this case will be xn minus 1 divided by 1 minus xn minus 1. Then if you write the multiplication on the right hand side, it will be alpha AB into x1 upon 1 minus x1 into alpha AB into x2 upon 1 minus x2 into alpha AB x3 upon 1 minus x3 into the last term will be alpha AB into xn upon 1 minus xn. Okay, so that means there are n number of terms involved. So there is multiplication of alpha AB n times. So that's why it will be alpha AB raised to n, because we are multiplying alpha AB for n times. So this will be alpha AB raised to n. Rest other terms will be now in the bracket. You can take alpha AB raised to n common. So alpha AB raised to n into x1 upon 1 minus x1 into x2 upon 1 minus x2 into x3 upon 1 minus x3 into the last term is xn upon 1 minus xn. So previously we got this, the left hand side is xd upon 1 minus xd into x1 upon 1 minus x1 into x2 upon 1 minus x2 into the last term xn minus 1 divided by 1 minus xn minus 1. The right hand side is alpha AB raised to n into x1 upon 1 minus x1 into x2 upon 1 minus x2 into x3 upon 1 minus x3 and the last term is xn upon 1 minus xn. Now let us equate the two sides, that is LHS is equal to RHS. So it will be xd upon 1 minus xd into x1 upon 1 minus x1 into x2 upon 1 minus x2 into the last term is xn minus 1 divided by 1 minus xn minus 1, that is equal to alpha AB raised to n into the terms in the bracket will be x1 upon 1 minus x1, x2 upon 1 minus x2 into x3 upon 1 minus x3 into the last term is xn divided by 1 minus xn. So you'll come to know that all the terms except the first one on the LHS is xd upon 1 minus xd and the last one on the right hand side, it is xn upon 1 minus xn. Apart from these two terms, all other terms they are going to get cancelled. Because they are present on both the sides. So for example, x1 upon 1 minus x1 is present on the left hand side and it is also present on the right hand side. x1 upon 1 minus x1. So that will get cancelled out. Same is the case with x2 upon 1 minus x2 and all other terms. So that means you are left with xd upon 1 minus xd, that is equal to alpha AB raised to n into xn upon 1 minus xn. All other terms since they are present on both the sides of the equation, they will get cancelled. So that is xd upon 1 minus xd, that is equal to alpha AB raised to n into xn upon 1 minus xn. So let us continue with this. So previously we got this xd upon 1 minus xd is equal to alpha AB raised to n into xn upon 1 minus xn. Let us do some so under total reflux. So since we are considering a column under total reflux, what are we going to what we know about this particular thing, and that is when the column is operating under total reflux, there are minimum number of stages. I am calling it as n minimum, and there is one reboiler. Minimum number of stages in the column and one reboiler. So if you have to understand this with the help of this diagram, so the last stage in the column will be the minimum number of that is possible. So if this is n minimum, so n minimum plus one reboiler. So that's why I'm saying under total reflux there are minimum number of stages in the column and there is one reboiler. So that means if you follow this equation, if n is equal to n minimum plus 1, that means you are traveling throughout the column, you are reaching n minimum stage, and then you are coming out of the column, going to the reboiler, and in the reboiler you will have the composition of the liquid is xw. That means when n is equal to n minimum plus 1, then xn is xw. That means after n minimum plus reboiler, you are arriving at the reboiler where the composition in the liquid solution is xw. So we are going to use this information. When n is equal to n minimum plus 1, xn is equal to xw. So let us use it. So that is xd upon 1 minus xd is equal to alpha AB raised to n minimum plus 1. Now I am replacing n with n minimum plus 1. If I do that, I will have to replace xn with xw. So xd upon 1 minus xd is equal to alpha AB raised to n minimum plus 1 into xw upon 1 minus xw. That is alpha AB raised to n minimum plus 1, that is equal to xd upon 1 minus xd divided by xw upon 1 minus xw. So I have brought this term on the other side. Now let us continue with this. So previously we got this equation. What is that equation? Alpha AB raised to n minimum plus 1, that is equal to xd upon 1 minus xd divided by xw upon 1 minus xw. Now what I will do? I will take logarithm on both the sides. So if I do that, it will be ln of alpha AB raised to n minimum plus 1, that is equal to ln of xd upon 1 minus xd divided by xw upon 1 minus xw. And if I use this logarithmic identity, that is ln of m raised to n is nothing but n into ln of n. So that this is logarithmic identity, and I'm going to use it on the left hand side of this equation. So n minimum plus 1, it will be now it will come as a multiplying factor with the logarithmic term. So it will be n minimum plus 1 into ln of alpha AB, that is equal to ln of xd upon 1 minus xd divided by xw upon 1 minus xw. And if you rearrange it, then you can write equation for n minimum. So n minimum plus 1 is equal to ln of xd upon 1 minus xd divided by xw upon 1 minus xw divided by ln of alpha AB. Then again you can use a logarithmic identity where ln of m minus ln of n is ln of m upon n. So in this case, ln of m upon n is ln of m minus ln of n. So if I use it, I'll be getting this equation. N minimum is equal to ln of xd upon 1 minus xd minus ln of xw upon 1 minus xw divided by ln of alpha AB, and this plus 1, when it comes on this side, it will be minus 1. So ultimately, I'm getting this equation, which can give me minimum number of stages in a typical tray column, and that equation is nothing but the Fenske equation. So in this equation, you can get the minimum number of stages in a typical tray column. So now you know how to find minimum number of stages in a typical tree bottom when it is operating under total reflux by using an equation. Earlier, you learned how to find it using the graphical method, McCabe-Thiele method. Okay? So in this way, you can derive the equation. Then the Fenske's equation, let me talk more about it. So we just got the equation. It is L minimum is equal to Ln of xd upon 1 minus xt, that is equal to Ln of xw upon 1 minus xw divided by Ln of alpha ab minus 1. Now this equation, first is you can use this equation when the components can form ideal solutions. This is one thing, because we have got this equation by using the definition of relative volatility, which was obtained for ideal systems. The other thing that you have to note over here is this equation is applicable when alpha AB is constant. This is the first thing. And even if there is mild change, if alpha AB moderately changed from bottom to top of the column, then what you can do? You can use the geometric mean of the two values. Value of alpha AB at the top and value of alpha AB at the bottom. So that geometric mean is given as alpha AB is equal to under root of alpha ABT into alpha ABB. Alpha ABT is the value of alpha AB at the top of the column, and alpha ABB is the value of alpha AB at the bottom of the column. So you can use this geometric mean. When can you do this? If alpha AB changes, but that change is a moderate change from top of the column to the bottom of the column. So if you can show this, so this is, let us call it as alpha AB average, because it is geometric mean. And how you are going to choose that? So if this is the column, then you use the value of alpha AB at the top. I'm calling it as alpha ABT, and then value of alpha AB at the bottom. And you take the geometric mean of these two values, and then you can use that mean as you can consider that to be constant, and then you can go for this equation. So in this way, now you know how to derive the Fenske's equation. You know this is applicable when the components involved can form ideal solutions. You know this can be used when the relative volatility is constant. If it changes moderately from top to bottom, then go and use the geometric mean of the values of alpha AB and at the top and at the bottom. So you can use this. So that ends my discussion for the derivation part. The other thing that this particular video was the limitation. Let us understand what are the limitations of the McCabe-Thiele method. First one is the method should not be used in the following cases. You cannot use this method in some of the cases, which are this: the relative volatility is less than 1.3. If relative volatility for the system is less than 1.3, don't use the McCabe-Thiele method. The relative volatility is more than 5. If the relative volatility of the system is more than 5, don't use the McCabe-Thiele method. Then, if the reflux ratio is less than 1.1 times the minimum reflux ratio, don't use. Again, you cannot use. If you try to use it, you are not going to get the correct results. Say when reflux ratio is less than 1.1 times the minimum reflux ratio, you cannot use McCabe-Thiele method. That is, you cannot use if the reflux ratio is less than 1.1 times of the minimum reflux ratio. Then you cannot use McCabe-Thiele method if the number of theoretical stages that is greater than 25. So if the number is greater than 25, you cannot use the McCabe-Thiele method. So these are 4 limitations for the McCabe-Thiele method. First is you cannot use it if the relative volatility is less than 1.3. You cannot use it if the relative volatility is more than 5. You cannot use it if the reflux ratio is less than 1.1 times the minimum reflux ratio. and you cannot use it when the number of theoretical stages is greater than 25, when the theoretical stages required are greater than 25. So with this, I end my discussion for this particular video. Here, I have discussed two things. One is I have discussed the derivation. Now, I am sure you will be able to derive the Fenske equation, and then many times you may have question on this. What are the limitations of McCabe-Thiele method? In GATE examination, any question on any one of these aspects may be asked, or even in interviews, they can ask this question: what are the limitations of McCabe-Thiele method? So the other method, which I'm going to discuss from my next video, the Ponchon-Severett method. So these limitations will not come into picture in that case. For now, I will end my discussion for the McCabe-Thiele method. I hope I have covered every aspect of the McCabe-Thiele method. All videos on McCabe-Thiele method are available on my YouTube channel. Please watch them. Tell your friends to watch those videos. Thanks for watching. Thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. And let us meet in my next video lecture. Well, I'll be starting my discussion on the Ponchon-Severett method. For now, have a nice day. Bye-bye.